Welcome to the deep dive. It is really great to have you with us today. We're diving into something fascinating again. Have you ever, been traveling, maybe bought some cool gadget, brought it home, and then, oh no, the plug's wrong, or the voltage? You probably reach for one of those little adapter things, right? Hoping it works and doesn't will fry your new toy. Or maybe you've just driven past those big gray metal boxes you see sitting up on utility poles. They kind of hum sometimes. I wonder what exactly they do. Well, today, that's what we're unpacking. Those incredibly important but often kind of invisible heroes of our electrical world, transformers. And nope, definitely not the giant robot kind, though the engineering inside is pretty futuristic in its own way.
Oh, absolutely. They really are the quiet giants, aren't they? The unsung workhorses powering everything. Most people, well, they never give them a second thought. But honestly, without them, our whole modern life, the lights, the screen you're maybe listening on right now, it would just stop. They play this foundational role, delivering power safely, reliably. But yeah, totally overlooked usually. They bridge that gap, you see, between huge power plants and the electricity we actually use.
Exactly. So our mission today for this deep dive is really to demystify these things, especially for you if you're just, starting to get curious about how electricity works. We want to break down this complex world of transformers into pieces that are easy to understand, really aiming for that beginner's level. So no confusing jargon, just clear understanding. The goal is you walk away feeling like, okay, I get that now, those little aha moments.
That's precisely it. Because transformers, especially the big ones, they can look pretty intimidating, right? All those parts, the sheer size.
Yeah.
But we promise the core ideas, the why behind each part, it's surprisingly intuitive once you break it down. And that's what we want to do, illuminate those essential whys, turn complexity into something, well, approachable. Think of it like we're taking careful baby steps in electricity, just like our source material suggests, guiding you through each bit nice and clear.
Yeah, exactly. And to make it super relatable right from the start, let's think about a simple example. That little household transformer, the one you might use to plug a 220-volt European device into a 110-volt US outlet, that small familiar thing. That's going to be our anchor. It'll help us understand every component we talk about today. It's like a mini version of the big guys. So, ready to jump in? Let's unpack this thing. Okay, so picture that little household transformer again. You plug it into the wall. Let's say it's a 220-volt outlet somewhere. That power needs to somehow become 110 volts for your American gadget. How does that magic happen? Well, first off, that incoming 220-volt electricity, it usually hits a fuse. That's like a little safety guard, right?
Exactly, a critical safety bit. It's designed to blow if too much current tries to surge through, protecting everything downstream.
Right. Then maybe it goes through a power switch, on, off, simple enough. And then the power finally goes into the heart of the transformer itself. It does its transformation thing and then comes out the other side, ready for your 110-volt appliance. That's the basic path.
And right at the absolute core of that path, whether it's that tiny converter or a massive substation transformer that weighs, I don't know, tons, you find two fundamental things. These are the absolute bedrock components that make voltage conversion even possible. You've got the iron core and you've got the copper windings. These aren't just, important parts. They are the transformer, essentially, the heart and soul of any transformer, big or small. Without those two, you just don't have a transformer, period. Now, of course, depending on what the transformer's for, how much power it handles, where it lives, you'll see other bits and pieces added, sometimes really precise safety gadgets, sometimes complex cooling systems, sturdy boxes to hold it all. But for this deep dive, especially since we're focusing on explaining it from that beginner's angle, we're really zeroing in on these two core materials. Understand the iron core and the copper windings properly, and you've basically cracked the code for understanding any transformer. They're like the universal starting point.
That makes total sense. Yeah, like learning the ABCs before you try to read, right? Start with the basics. Everything else builds on that. Okay, so let's really dig into these fundamentals then, starting with the iron core. You called it the heart and soul, the backbone. So if we could, slice one open, what does it actually look like? I'm picturing, I don't know, a solid block of iron. But I get the feeling it's probably more complicated than that, is it? And the big question, why iron? What's so special about iron for this job?
You're right, it's definitely not just a solid lump. Visually, yeah, if you could peek inside, the iron core Looks more like a carefully stacked set of metal sheets, often arranged in like a rectangular shape or sometimes an E shape. It really forms the main body of the structure. And the reason iron, specifically certain types of iron, is so critical, it's all about its amazing relationship with magnetic fields. See, when electricity flows through those copper coils wrapped around the core, it creates a magnetic field, like an invisible force swirling around the wire. The iron core's job, its crucial role, is to act like a super efficient guide for this magnetic field, a pathway. It basically grabs that magnetic influence, concentrates it, and channels it really precisely from the the primary side over to the output side, the secondary. If you didn't have that iron path, magnetic field would just kind of spread out, get weak, would dissipate into the air. The transformer wouldn't work well at all. It's like, yeah, trying to shout across a field versus using a megaphone, maybe. The iron is the megaphone for the magnetic field, and this knack for guiding magnetic fields. Engineers have a word for it: permeability. Ah, don't let the term scare you, though. Just think of permeability as how easily a material lets itself become magnetized, and crucially, how well it can pass that magnetic force along. Like a highway for magnetism. High permeability means a really smooth, efficient highway. Low permeability may be a bumpy dirt road. So the higher the permeability of the iron core, the better. It makes sure almost all the magnetic field created by the first coil gets transferred powerfully to the second coil. Less waste. It's about making sure all that magnetic effort actually does the job.
Okay, this is where it gets really cool, I think. Because, like I suspected, it's not just a solid block. If efficiency is so key, I bet engineers have done some clever things to make that iron core even better, right? To stop energy loss. I mean, why not just a solid chunk? Seems easier to make, maybe.
Oh, you've hit on a really clever point. It reveals some serious engineering smarts. It's absolutely not a solid block, and for really good reasons. There are two main tweaks they make to the iron core to boost efficiency and, crucially, cut down on energy waste. And energy waste here means electricity turning into heat you don't want. Wasted energy, wasted money, and it wears the transformer out faster. Okay, modification number 1 is about the iron itself, its recipe. They add a bit of silicon, usually about 3 to 5%. It's not random, it's a carefully tuned amount. And this silicon is there specifically to fight something called hysteresis loss. Hysteresis loss. Sounds complicated, but think of it like this. The electricity in the coils is alternating current, right? AC. So the magnetic field in the core isn't steady. It's constantly flipping direction. Magnetize this way, demagnetize, magnetize the other way. Really, really fast. 50 or 60 times a second. Now, if the iron kind of resists those flips, if it's magnetically sticky, it takes energy just to force it to change its magnetic state over and over. That energy gets lost as heat. Like bending a paperclip back and forth, it gets warm, right? Adding silicon makes the iron magnetically softer, less resistant to these rapid reversals, less internal magnetic friction. So less energy gets wasted as heat during those constant magnetic flips. The transformer runs cooler, more efficiently, more power gets transformed, less gets wasted.
That totally makes sense. Making the iron more, I don't know, magnetically flexible to save energy. Cool. But you said there was a second modification. What's that? And why stack up lots of thin plates? That sounds like way more effort.
It is more manufacturing effort, definitely, but it's an absolutely brilliant solution for tackling another kind of energy loss. So the second tweak is the structure of the core. Instead of being solid, it's made by stacking up lots and lots of very thin iron plates. We're talking thin, like maybe 0.35 millimeters, thinner than your credit card. But here's the genius part. Each thin sheet has a super thin coating of insulating material on its surface, like a varnish or something, creating an insulating film between every single layer. This isn't just convenient, it's essential. The whole reason for these thin insulated layers is to stop something called eddy currents. Imagine tiny little unwanted whirlpools of electricity getting induced and swirling around inside the iron core itself. If it were a solid block, these eddy currents could form big, strong loops within the metal, generating a lot of heat and wasting tons of energy, like tiny short circuits running wild inside. But by using these thin sheets, each separated by that insulating film, you break up the path for those currents. Any current induced has to stay within its own tiny, thin plate. It can't form those big, wasteful loops across the whole core. It essentially chops those potential whirlpools down into tiny, harmless ripples. It drastically cuts down on heat and energy loss. Super clever way to stop the core from basically cooking itself.
Wow, that's incredible. So much cleverness just to make the core work better. Like breaking a river into tiny channels. You also mentioned there are different ways the core and coils are arranged, like inner core versus outer core types. What's the difference there? How does the physical layout affect things?
Yeah, this is about the architecture, the physical shape. And it's all about guiding that magnetic field as effectively as possible. Let's start with the inner core type. Picture a central iron core that's kind of like a rectangular frame, or maybe just columns. In this design, the primary coil and the secondary coil, the copper windings, they're put on separate sides or legs of this iron frame. One coil here, the other over there. Now, this way is pretty straightforward to build, but it has a drawback. It tends to have more leakage flux. Think of the magnetic field lines like invisible roads carrying the magnetic energy. Ideally, they all stay inside the iron core, going from the first coil to the second. But with the inner core type, a noticeable chunk of those magnetic lines actually kind of escapes, looping out into the air instead of staying in the iron to do their job. This leakage means some magnetic energy gets wasted. It doesn't contribute to inducing current in the secondary coil, like, a hose with leaks. It reduces the transformer's efficiency, especially for bigger ones where every bit of lost energy matters. Okay, now compare that to the outer core type. Here, the windings are usually layered, one inside the other, but critically, they're wrapped around the same central part of the iron core. Imagine the iron core forming more of a shell or frame around the coils. The coils are nestled together in the middle. This might seem like a small difference, but magnetically, it's huge. It results in significantly less leakage flux. Because the coils are closer together and the iron core forms a more complete magnetic path around them, the magnetic field is much better contained within the iron. Fewer lines leak out. This means a much more efficient transfer of energy from primary to secondary. It's a great example of how design choices directly impact performance. That outer core type, by minimizing leakage, is often the go-to for larger, high-efficiency transformers, where squeezing out every last bit of performance is really important. Shows how engineers think about the arrangement just as much as the materials.
Right, so the iron core is the magnetic highway guiding the force. Then the windings, those are the actual roads for the electricity itself, carrying the current, creating the magnetism. What are they usually made of? And do they change shape or form depending on how big the transformer is?
Absolutely. The windings are the conductors handling the flow of electricity, and they're almost always made of copper wire. Why copper? Simple. It's a fantastic electrical conductor. Lets electricity flow really easily with very little resistance. Less resistance means less energy wasted as heat just from the current flowing through the wire itself. Maximizes efficiency. Now, for smaller transformers, like our little travel converter, plain old round copper wire is pretty common. Works just fine. Like, the wire inside a lamp cord just wound many times. But when you scale up to bigger, more powerful transformers, you see a smart change. Our source mentions they often use flat square wire. Instead of round, the wire itself is flat and rectangular or square in cross-section. And the reason for that shape, it's all about packing density. Imagine trying to bundle round straws versus square sticks in a box. With round wires, you always get those little gaps between them, right? Wasted space. But flat square wires, they can pack together much more tightly, almost like bricks, less wasted space. This means you can fit more copper conductor material into the same area, which is great for big transformers carrying huge currents, more current capacity in the same size, basically. Reduces losses, too. It's a neat little optimization for big jobs.
That makes perfect sense, getting the most conductor into the space available. Smart, but okay, these wires are wound round and round, layer after layer, sometimes thousands of turns. How do they stop them all from touching and shorting out? Seems like just one little scrape could cause a massive problem if they weren't separated somehow.
You're absolutely right to think about that. It's a huge concern and highlights why insulation is just so critical everywhere in a transformer. Every single strand of copper wire, whether it's round or that flat square type, is carefully coated with an insulating material. Not just any stuff materials chosen for high electrical resistance, durability, heat tolerance. Often it's a thin layer of enamel, like a tough baked-on paint. Or sometimes you see layers of special paper tape, or even cotton thread wrapped around it, especially in older or oil-filled designs. And this insulation on each wire is absolutely fundamental. Think about it. Thousands of turns of wire right next to each other, but potentially at slightly different voltages. If that thin insulation layer wasn't there on every single turn, the wires would touch. Direct electrical contact, boom, instant short circuit within the winding. Current takes the easy path, bypasses the coil, massive heat, sparks, maybe fire, complete failure. So that simple coating is what keeps the electricity flowing along the long intended path of the coil, doing its job instead of taking a disastrous shortcut. It's the quiet guardian. And there are different ways they actually wind these coils too, depending on the transformer. Our sources mention two main methods: direct winding and pre-wound coil. Direct winding is pretty much what it sounds like. The insulated wire is wound directly onto the iron core structure itself. Finish one winding, insulate it, then wind the next one over it. This is often used for smaller transformers, like our household one. Simpler, maybe more manual or semi-automated. Voltage levels aren't quite as extreme. The pre-wound coil method is different. It's often used for larger, higher voltage units where precision is paramount. Here, the coils are wound first, separately, maybe onto a strong insulating tube or a mold. Like winding yarn onto a bobbin, but much more precise. They get insulated and prepared as a complete self-contained unit. Then, this finished coil assembly is carefully mounted or slid onto the iron core. This allows for maybe better quality control, tighter winding, more robust insulation processes before assembly. And interestingly, the sources note that for those inner core iron structures, they typically use cylindrical coils that fit nicely onto the core legs. But for the outer core types, they often use rectangular or flattened coils to fit efficiently inside that outer iron frame, matching that square wire concept. So you see this cool interplay. The core design influences the best winding method and even the coil shape. It's all connected in the design.
Wow, okay, so much detail just in the core and windings. It really is like a hidden feat of engineering inside that box. Now, how does the electricity actually get out? You've got these super carefully insulated wires inside, maybe sitting in oil, inside a big metal tank. How do the wires pass through that metal tank wall safely without touching the metal case and causing like a massive short circuit to the outside world? Seems tricky.
It is tricky, and it requires a dedicated component, the bushing. Think of a bushing as a specialized insulating tunnel or pipe. Its one job, its vital function, is to provide a safe, heavily insulated path for the live electrical conductor to pass through the grounded metal wall or casing of the transformer. Without it, the live wire hits the metal case. Instant short circuit to ground. Very dangerous, big problems. So the bushing is the safe gateway, connecting the inside world of the transformer windings to the outside electrical grid or cables, making sure electricity only goes through the conductor, not the casing. The most common type you'll see, maybe on pole transformers or substation equipment, is the single-type bushing, usually made of porcelain, that ceramic material you see on power lines, or sometimes tough synthetic resins. These are great electrical insulators. It's basically a sturdy, often ribbed or skirted insulating structure with a metal conductor running right down the middle. Isolates the conductor from the metal flange where it mounts to the tank. Now, our source also mentions other types briefly, like compound bushings, oil-filled bushings, condenser bushings. Basically, as voltages get really high, like hundreds of thousands of volts, you need even more sophisticated designs. A condenser bushing, for instance, has multiple layers of insulation and conductive foil inside, carefully designed to distribute the electrical stress evenly. Prevents the insulation from breaking down under extreme pressure. It just shows that even getting the power out safely requires some pretty advanced engineering, especially at high power levels.
Fascinating. So it's all about controlling the path, making sure electricity stays exactly where it should. And we keep coming back to insulation, don't we? On the core laminations, on the wires, now the bushings. Why is it so incredibly important? It seems like the #1 priority in transformer design. What actually happens if it breaks down?
It really is paramount. Insulation is the absolute guardian of safety and reliability. You can't overstate it because electricity, especially high voltage electricity, always wants to find the easiest path. Insulation forces it to take the path we want it to take. So inside the transformer, you need robust insulation in all those key spots, between the iron core and the windings touching it. Between the primary and secondary windings themselves, got to keep input and output separate. And like we said, between layers of windings, and even between each individual turn of wire within a winding, every part needs to be electrically isolated from its neighbors unless it's meant to be connected. And if that insulation fails, if it's damaged or just gets too old and weak or gets punctured, the consequences are immediate and usually pretty dramatic. You get major electrical faults, usually short circuits, current flows where it shouldn't, uncontrolled. This means massive sudden current surges, extreme overheating, violent arcing like internal lightning, potentially fire, and catastrophic damage to the transformer itself. It can also trip protective breakers way upstream, causing blackouts, and potentially damage other expensive grid equipment connected to it. So there's a direct line. Good insulation equals safety, reliability, and keeping lights on. It's the invisible shield.
Okay, but transformers are famous for lasting ages, right? Decades sometimes. Does the insulation just last forever? Or does it eventually wear out, given all the heat and electrical stress?
That's a great question. And you're right, transformers are workhorses, built for long life. 20, 30, 40 years isn't uncommon at all. But no, unfortunately, insulation doesn't last forever. It does degrade naturally over time. It ages. It's a slow process usually, but it happens. Factors like heat, moisture getting in, oxygen, even just the constant electrical stress itself, they all take a toll. Think of it like the materials getting brittle or chemically changed over decades. This degradation is cumulative. Little bits of damage add up. Environmental factors play a role: humidity, contaminants in the air, mechanical stresses to vibrations, the expansion and contraction cycles from heating and cooling. As the insulation degrades, its ability to withstand voltage gets weaker, it becomes more prone to breaking down under stress. And this directly impacts the transformer's lifespan and how reliably it performs. It's like a slow, quiet countdown happening inside. And this brings us to something absolutely critical: temperature. Heat is the main enemy of insulation. It dramatically accelerates that aging process. It's like baking something in an oven versus leaving it on the counter. Heat speeds up the chemical reactions that break down the insulating materials. Because of this, there are really strict rules about transformer operating temperatures. You do not want them running too hot for too long. Overheating kills insulation, plain and simple. Which leads us perfectly into why cooling is so vital, and why maintenance, like checking the condition of things, is essential to catch degradation before it causes a failure and to help these things reach their full, long lifespan.
Right. Okay. Cooling systems. If heat is the big enemy of insulation and transformers naturally generate heat, why do they get hot? Where's the heat actually coming from? And what are the main ways we fight it?
Good question. The heat comes from those losses we touched on earlier. It's basically inefficiency manifesting as heat. When electricity flows through the copper windings, even though copper is a great conductor, it still has some resistance. That resistance turns some electrical energy into heat. We call that copper loss or winding loss, like an electric heater element, but much less intentional. And similarly, inside the iron core, that constant magnetic flipping, the hysteresis loss we talked about, and those tiny eddy currents, even though we minimize them, they also generate heat. That's iron loss or core loss. So these losses from both the copper and the iron mostly get released as thermal energy, waste heat. It's an unavoidable side effect of the physics involved. And like you said, this heat is bad news. It raises the temperature inside, obviously. But the real problem is what it does to the insulation: speeds up aging, reduces lifespan, lowers efficiency. Heat is just detrimental all around. So having an effective cooling system is absolutely essential, non-negotiable. Its job is simply to get that heat from the inside, where it's being generated in the core and windings, and move it to the outside environment, away from the transformer. Keep the internal temperature down, keep the insulation happy. There are different ways to do this. Cooling methods are usually classified based on 1, what's used to move the heat, like air or oil, and 2, how it's moved, like natural circulation or using fans and pumps. So bigger transformers with more heat need more powerful cooling than smaller ones. The system is matched to the need.
That makes total sense. Fight the heat to protect the insulation. And for the bigger ones, it's not just air moving the heat, right? You mentioned that special oil earlier. What's the deal with this insulating oil? Why is it so crucial for the big guys?
Exactly. For larger transformers, the ones handling serious power, just relying on air blowing past isn't enough to get rid of all the heat. That's where oil-immersed transformers come in. The name says it, all the core and windings are literally submerged inside a tank filled with a special mineral oil, usually called transformer oil or insulating oil. And this oil does 2 critical jobs at once. It's a real multitasker. Job number 1, it's an excellent electrical insulator. The oil fills all the gaps, creeps into every little space around the windings and between components. It has very high dielectric strength, meaning it strongly resists electrical breakdown. It provides way better insulation than air alone could in those tight spaces. This helps prevent internal arcs or shorts between high voltage parts. It's like an extra layer of electrical protection. Job number 2, it's a fantastic cooling medium, much better than air at absorbing and transferring heat. The heat generated by the hot windings and core gets transferred directly into the surrounding oil. Then the oil circulates often just by natural convection. Hot oil rises, cooler oil sinks, carrying that heat away from the hot spots towards the walls of the tank. The tank walls, sometimes with fins or separate radiators attached, then transfer the heat to the outside air. This constant circulation of oil keeps the core and windings much cooler than they would be in air alone. Absolutely vital for large transformers to avoid overheating.
Wow, dual purpose? Insulates and cools. That's pretty neat stuff. Sounds like magic oil. But is it permanent? Does it just sit there doing its job forever? Or is it more like, say, the oil in my car engine that needs checking and changing eventually?
That car engine oil analogy is perfect. Because no, transformer oil is definitely not permanent. It degrades over time and absolutely needs to be monitored and eventually replaced. Just like engine oil breaks down from heat, contamination, and use, transformer oil suffers a similar fate. It's an unavoidable aging process. Why does it degrade? Well, a few reasons. The constant heat from the transformer itself slowly breaks down the oil's chemical structure. Then there's something called breathing. As the transformer heats up, the oil expands, pushing air out. When it cools, it contracts, sucking air in. That means the oil comes into contact with oxygen and moisture from the outside air, and both oxygen and water are bad news for insulating oil. They cause oxidation and contamination. Plus, impurities can form as the oil itself breaks down chemically over years of service, and when the oil degrades, it loses its superpowers. Its cooling ability gets worse, so the transformer runs hotter. More importantly, its insulating property, that dielectric strength, drops significantly. It gets weaker, less able to prevent electrical breakdowns. Degraded oil can also form sludge, like sticky gunk, that can coat windings and block cooling ducts, making things even worse. And if the oil gets really bad, it dramatically increases the risk of a catastrophic failure. An electrical surge, or even just normal operation with badly degraded oil, could lead to internal arcing, short circuits, basically a transformer meltdown.
Yikes. Okay, so given those serious risks, what does that mean for keeping these critical machines running safely for decades? What's the maintenance look like for this oil?
It means that regular, careful maintenance of the oil is absolutely critical. It's a non-negotiable part of ensuring transformer longevity and grid reliability. Just like you get your car's oil checked, technicians have to periodically test the transformer oil. They take samples and run tests to measure things like its oxidation level, how much it's broken down chemically due to air exposure, how spoiled it is, basically. They also check its resistivity, how well it resists conducting electricity. High resistivity is good. It means it's still a great insulator. Low resistivity is bad. These tests paint a picture of the oil's health, telling us if it can still do its jobs properly, and if the tests show the oil is too degraded, if it's lost its critical properties. Then, yeah, just like an oil change for your car, the old degraded oil has to be completely drained out of the transformer tank. Often they'll flush the system too to get rid of any sludge. Then it's refilled with fresh, clean, new insulating oil that meets all the specifications. This restores the transformer's cooling and insulating performance back to where it should be. It's a vital, active maintenance step that directly prevents failures and helps these things last for their full expected lifespan, keeping those silent giants healthy.
This has been genuinely fascinating. We've really taken the transformer apart piece by piece, haven't we? Started with that iron core, learning about the silicon making it magnetically softer, the amazing thin lamination stopping those eddy currents, the difference between inner and outer core designs for efficiency, then the copper windings carrying the current, and how absolutely vital the insulation is on each wire. We look at how the power gets out safely through those specialized bushings, and just keep hammering home how critical insulation is everywhere inside. And then wrapping up with how they fight the heat they generate through cooling systems, especially using that multitasking insulating oil in bigger units. What really strikes me is how everything is connected. Every single part plays a specific, crucial role for safety, for efficiency, for making these things last for decades. It's pretty amazing how fundamental physics principles lead to these incredibly complex but reliable machines. And yeah, looking at it from that beginner's viewpoint, focusing on the why, really helps it all make sense.
It really does. And this deep dive, it's not just about nuts and bolts, is it? It's about appreciating the incredible, often invisible infrastructure that powers everything we do, understanding the engineering that lets us flip a switch and have light or charge our phones or run entire cities. It's quite profound when you think about it, and it really highlights how essential that careful design and ongoing maintenance, checking the oil, watching temperatures, using the right materials really is. It keeps everything running smoothly and safely. Those aha moments, like realizing why they use flat wire or why oil is needed for big transformers, they really show the thought that goes into these things. It's elegant engineering working silently all around us.
Definitely. So, knowing how vital all these little details and maintenance steps are, it leaves me with a kind of interesting thought experiment for you, our listener. What do you think might happen to our power grid if, say, just one of those seemingly basic maintenance steps, like regularly testing and replacing the insulating oil, was consistently skipped or overlooked on a really large scale, thousands of transformers? The knock-on effects of that kind of widespread, maybe subtle neglect could be pretty significant, couldn't they? Something to ponder.
Absolutely. It really underscores that even with mature technologies like transformers, vigilance and continuous improvement are key. And it makes you wonder, doesn't it? Thinking about all this maintenance, how might future innovations, maybe new materials with even better insulation properties or smarter sensors embedded inside transformers to monitor their health in real time, how might those things further extend the life and efficiency of these silent giants? Maybe make some of this maintenance easier or even less necessary down the road. The quest for better reliability never really stops.
Absolutely. The future of energy is always evolving. Well, thank you so much for joining us on this deep dive into the truly fascinating world of transformers. Keep exploring, keep asking questions, and stay curious about the amazing engineering that powers our world, often right under our noses. We'll catch you on the next deep dive.